Can you guys hear me? Okay, good. Okay, I'll share the content and we can start. Okay, can you see the PDF now? All right. It's good. Okay, so let's move on to to the next part in a thermal oxidation process. So last time we've gone through the introduction to the process. So let's recap a few things about um, the basic of thermal oxidation. So how many types of thermal oxidation can we do to be able to grow our oxide? How many types can we do? Two, okay. Name them. What are the two? Wet and dry, okay. So what's the difference between wet and dry oxidation? What's the main difference between wet and dry? Wet uses H2O and dry uses O2 gas. Yep, good name. So kita pakai wet precursor by water vapor. Okay, water vapor, not water vapor. We vaporize the water by a bubbler. Okay, we'll see later on. And for dry process, we use dry oxygen. Okay, how about the function of oxide? What are the general functions of oxide? Why do we normally use oxide for our fabrication? Apa role-nya? Give me a couple of roles of oxide or functions of oxide. Why do we grow oxide in our fab? Anyone? Zuriati? Kenapa kita grow oxide? What is the function of oxide? Boleh unmute? Zuriati? Kenapa kita grow oxide? Syairah? Syairah, why do we have oxide?
Hello, doctor.
Yeah, hello. Okay, why do we have oxide?
To get high quality oxide layer.
Okay, but why do we need the oxide for our fab process? What is the role of the oxide? What is the function of oxide? Nak guna dia untuk apa? Apa yang paling obvious? Use of oxide. Yes, dielectric, insulator. Yep, good. Dielectric, insulator kita nak letak dia kat mana ni dalam structure kita? If you talk about IC fabrication, then why the oxide? Kita pakai dielectric tu kat mana? If you talk about your MOSFET, kat mana dia punya dielectric tu? For insulator? Be specific. Yes, below the gate, right? Yes, be specific. When you answer, be specific. Nanti kalau you go through interview, you kena be specific ya. Itu dia jawab general. Okay, you have to be specific. Pinpoint your what do you mean? Below the gate. So right below the gate is dielectric or insulator. Okay, apa lagi role dia? Apa lagi role oxide for our fab process? Give me one more, then we proceed to the next one. Jenny, what's another one? What's another role of the oxide?
To prevent tunneling.
To prevent tunneling, yep. Therefore, it has to have sufficient thickness. Okay. All right then. So there are a few more roles, preservation and few more, right? You boleh tengok balik kita punya previous notes. So let's move on to the next part. So this is more or less a thermal oxidation equipment. This old version, tapi yang new one pun dia tak banyak beza. So it looks more modern and it can do more stuff. This is, if you see on the left, is a triple stack furnace. Right, triple stack maksudnya dia ada tiga layer. So it's called a furnace because it has to run a high temperature process. So typically 900, 1000 for a long time. So you're going to have your quartz boat to hold your wafers. So it can be horizontal tube, it can be vertical tube to run the process. If you talk about a wet thermal oxidation process, the simplest version that you can see is this. It's on the slide. In fact, you can also see this in our lab, in our furnace lab, dekat ground floor, where you can use a water bubbler to vaporize water in order to get water vapor before it is sent into the furnace or it is sent into the tube for oxidation process. So the configuration of the furnace is illustrated below there. You have a carrier gas, then you have water vapor after it has gone through the water bubbler. So then the water vapor comes into the tube. In this case, it is a horizontal tube, and then you have your wafers on quartz board, and the tube is encapsulated by hot wires in order to ram the temperature to your desired temperature to do oxidation. Okay, that's how it works. On the other hand, for a dry oxidation process, so this is the representation of the process. So you normally pass the oxygen through, dry oxygen through the tube, and then the inside of the tube is exactly the same as what you saw on the previous slide. So you have your wafers, you have your quartz board, and then the tube is encapsulated by the heater to ram the temperature to the desired temperature. Okay, during the oxidation process, we're gonna see what is exactly happening during the process. But when you say it's an oxidation process, you don't actually just grow the silicon dioxide on the silicon, but rather the part of the silicon is actually consumed during the process for you to grow oxide. So that means when you are actually growing the oxide, to be able to do that, you need to consume the existing silicon from the silicon wafer to be able to grow your new oxide layer. So typically during the process, you can see that your silicon dioxide, for example, is on top and your silicon is at the bottom. So normally the ratio of the consumption is about 55-45, where some 45% of your of the grown oxide is actually coming from the silicon. Okay, so maknanya you punya level of original silicon tu yang is as illustrated there. That's the original surface of your silicon. But as the process goes on, the oxide actually consumes some of your silicon, so it actually grows into the silicon to be able to grow the final oxide. So actually final oxide is partly silicon, the original one, right? The original silicon. So it's 55-45. So that means if you have your silicon dioxide to be about 10%, for example, so that means about 55% of the 10 nanometer is the new oxide, and 45% of the silicon dioxide is actually from the silicon itself. So you eventually end up with 10 nanometer. So it's maybe it may be formed by 5.5 nano of the new one and 4.5 nano of the silicon. So in total, they make your whole oxide thickness. So in comparison, if you're talking about depositing a layer of silicon dioxide, katalah you ada wafer kat sini. This is your cross section of your silicon wafer. Kalau you nak grow a new layer of oxide, assuming this green is oxide, you can also deposit the oxide on the silicon. You will deposit. So this can be done by electron beam evaporation system, sputtering, and maybe CVD as well. So you can deposit the oxide on silicon. But in this case, it's called deposition process. It's not growth process. It's not oxidation. Bukan growth. It's not oxidation. Sebab apa? Apa bezanya? The difference is when you deposit a layer of oxide, the very same layer, SiO2, you are actually adding the layer on your silicon. Maksudnya kalau you nak deposit, you want to have your oxide to be 10 nanometer eventually. So then you need to deposit 10 nanometer of SiO2 by maybe sputtering or CVD on the silicon wafer to be able to get your 10 nanometer of silicon dioxide or SiO2. And it is based on thin film deposition process. So it's deposition, it deposited on the silicon. On the other hand, what we're learning now is called oxidation, where to be able to get this 10 nanometer, you actually need to get some of the oxide from the original silicon. So kalau deposition tadi, kita introduce completely new 10 nanometer from a new layer to on your silicon wafer. But thermal oxidation consumes your silicon to be able to produce your SiO2. Tapi deposition dia tak consume, dia just macam tambah layer je lah, tambah coating dia on the silicon. So okay, is it understandable? Faham tak the difference between having your SiO2 by thermal oxidation versus deposition by thin film methods? Is it okay? Understood or not clear? Okay, clear, right? So thin film deposition process do not consume your silicon, but thermal oxidation consume your silicon, right? Okay, we're gonna look at the kinetics of the silicon dioxide growth. So this is actually what's happening during the process. So apa yang kita tahu tadi, we have, for example, if you use your dry oxygen in a dry ox process, so you pass through your oxygen, masuk dalam your punya tube furnace, then eventually you're going to have maybe, I don't know, 10 nanometer of silicon dioxide, and that's it. So the kinetics of the silicon dioxide growth explains what's actually happening before you have the 10 nanometer oxide. what does it take for you to have the 10 nanometer eventually? So it's the intermediate steps, if you like, to be able to come to the 10 nanometer at the very end of the process. So basically, there are three steps happening during the process. The first one is oxidant, for example, your O2 or your H2O vapor reacts with silicon atoms. So because you firstly have your silicon wafers and silicon atoms, basically, so you don't have any oxide yet, assuming you have removed your native oxide before the process. Tapi kalau you start off dengan native oxide ataupun you dah ada oxide layer, the reaction will be different because you already started with your oxide on the silicon. So now we assume that you have before the thermal oxidation, you have already removed the native oxide. Native oxide means yang naturally grown oxide yang 1 to 2 nanometer kan. So you have gone to the HF dip, completely remove the native oxide, so you are left with pure silicon to be grown with SiO2 in oxidation process. So what will happen as the first step is oxidant, for example, O2 gas, will firstly react with your silicon atoms. And then what's going to happen next is silicon atoms are going to be consumed by the reaction as per the 55-45% rule just now. So we're going to see that the silicon dioxide actually grows into the silicon to be able to produce SiO2, and eventually layer of oxide forms on the silicon surface. So yang kita nampak hanyalah step tadi. Lepas kita letak oxygen dalam tube. So after, I don't know, maybe you're running at 950 degrees C for like 1 hour at some flow rate of nitrogen or oxygen. Then eventually after 1 hour, you get your desired oxide thickness. So this explains what is actually happening before you have the 10 nanometer of your oxide. So basically there are three main steps. So the first one is also called gas diffusion, where you supply your dry oxygen to the tube to be able to start the reaction. Okay, we're gonna see a little bit more detail later on, but this is the brief summary. And what's happening next is solid state diffusion, the yellow color there, where the silicon atoms are going to be consumed by the reaction, where the vapor or the dry oxygen, the oxygen atoms or the precursor material actually diffuses into silicon to be able to consume the silicon. So maksudnya perlu ada diffusion guys tu. So that's why we call it solid state diffusion, where the oxygen atom has to diffuse through the silicon to be able to consume. And then eventually we're going to end up with silicon dioxide formation. Barulah you akan ada formation. Okay. So there are three main steps in essence. So apa yang terjadi? We're going to go through one by one. So the first step is also called linear step. It's called linear parabolic step. Tapi the first one will be linear. The second step will be parabolic. There are two main phases. We're going to see why too. So the first one is the linear stage of the oxidation, where chemical reaction between silicon and oxidants just started at the wafer surface. Maksudnya you are the wafer surface, then you're having O2 coming in, and then the reaction starts. So that's the very first step. The reaction is limited by number of silicon atoms available to react with oxidants. So your number of silicon atoms on the surface will determine the reaction rate. So the more atoms that you have on the surface of silicon, so the higher will be the rate or the oxidation rate. So the lesser atoms you have on your silicon will produce lower oxidation rate. Bila saya sebut higher or lower number of silicon atoms, what comes to your mind? What could be the difference between when do you get higher number of silicon atoms and when do you get lower number of silicon atoms? What do you think? The reaction is limited by the number of silicon atoms. Bila kita ada higher silicon atom, bila kita ada lower silicon atoms? If you can recall what we learned last time. Bila kita ada higher number of silicon atoms, anyone knows? Bila, anyone? Any ideas? Inas, any ideas? When do we get higher number of silicon atoms and when do we get lower? Can we plan the number of atoms before the process? Inas, any idea? Izian, any idea Izian? Bila kita punya number of silicon atom higher or lower? What determines that? Higher surface area? Okay, makes sense. Okay, what else? When do you get higher surface area? Bila you ada higher surface area, how do you get higher surface area? Can you do that? No idea? How about this? How about this? 100 versus 111 orientations of the silicon wafers. Which one has higher number of silicon atoms? Kita dah belajar kan 386 last time. Which one is more packed? Any guess? We learned this when we talk about mobility of carriers. Yeah, it's 111. 111, eh? The denser one is 111. So this is where you gonna see the difference between the oxidation rate. Kalau you guna wafer 111 versus 100, then you're gonna end up with different oxidation rate. Then if you run the process at the same temperature, same time, two different wafer orientation, you're gonna end up with different oxide thickness at the end due to the number of silicon atoms difference. Okay, so 111 has higher number of silicon atoms, it's more packed, therefore the rate will be higher for 111 in comparison to 100. So yeah, this is how you design the oxidation thickness and stuff like that. So you can actually design that by using different wafers of different crystal orientation. So the first step, let me recap, the first step is limited by the number of silicon atoms available to react with oxidants. So if you have 111, so more atoms available for the reaction. If you use 100, there's less atom available for the reaction. So during the first 50 nano or 500 angstrom, so one nano is 10 angstroms. So during the first 50 nano of the oxide grows linearly with the time. So the growth rate is actually linear if you plot with time. So exceeding 50 nano is going to show a slightly parabolic shape. So it's no longer linear. We're going to see why. So the growth rate begins to slow down as oxide layer growth. So the moment you have thicker oxide, to be specific, somewhere 50 nano or more, so we're going to see slower rate of growth of the oxide. So the first 50 is linear and the next one is no longer linear. So right, the parabolic stage is the second stage, if you like, if you plot linear versus parabolic. So it begins when 100 nanometer of oxide has been grown on silicon. Well, you can argue it's 50 or 100. So it depends on the process. So most likely somewhere 100 is already parabolic. Probably somewhere 50 to 100 is the intermediate steps. Okay, so it begins when 100 nanometer of oxide has been grown on silicon. Maybe you can see the inflection point beyond 50 nano already. Silicon atoms are no longer exposed directly to the oxidant. So apa jadi kat sini ialah as you grow your oxide, you have your wafer, then you have your oxide. So assuming this one is 50 nano thick, so you have your oxide on your silicon. As the process grows further and further, so you punya oxidant tu masuk ke atas kan, you punya dry oxygen, maybe oxygen gas, for example, instead of the water vapor. So bila you ada oxygen kat sini, dia nak masuk untuk grow oxide. Remember, the process is about consuming the silicon to be able to grow the oxide, the successive oxide. So at this point, if you already have some thickness of oxide, you punya oxygen gas kat atas ni dia tak ada direct access to the silicon there. Because the reaction tadi start bila dia ada contact dengan silicon atoms kan. But at this point of time, the dry oxygen, the oxygen atoms, do not have direct access to the silicon atoms. Instead, they have to diffuse through this oxide layer to be able to reach the underlying silicon to further the growth. So maksudnya dia lambat sikit lah sebab dia ada satu barrier yang dia lalu kat sini 50 nano or so to be able to get to the underlying silicon to continue the process. So that is what slows down the process. So that's why if you like, the first step is the linear step because the oxygen atoms here have direct access to the silicon to start the growth process, and as the oxide thickness grows further, so now the oxygen atoms have no direct access to the silicon but have to diffuse through the existing silicon dioxide to be able to reach silicon to further the growth. Therefore, silicon are no longer exposed directly to this oxidant, and oxidants now need to diffuse through the oxide to reach the silicon to further the process. Now the reaction is limited by the diffusion rate of the oxidant through the SiO2 to be able to get to the silicon. So that makes the rate reduces and follows parabolic model. Okay. So this model is named as Dilgrove model. So kita akan panggil model ni sebagai Dilgrove. So bila saya sebut Dilgrove is actually reflecting linear. So kalau you plot graph oxide thickness versus time, Y is oxide thickness, X is time. So you're going to see like this from your side. You're going to see something like this. You're going to see linear, and then for the first phase, for the thin version of oxide, then you're going to see it goes down like that, parabolic. Sebab waktu ni oxide thickness dah tebal, so oxygen dari depan ni dia nak kena diffuse through the oxide to get to the silicon to be able to continue the reaction. And this is called Dilgrove model. Okay, so Dilgrove model mathematically describes the growth of an oxide layer on the surface of a material. So in particular, this is silicon. So it's used to predict and interpret thermal oxidation of silicon in semiconductor fabrication process. So the model was first published back in 1965, just like Moore's law, so around 1965 as well, by Bruce Deal and Andrew Grove. Both of them work in Fairchild Semiconductor at the time. So it's still being used until today. Okay, so dah lama model ni. So model ni basically they used to predict the growth of the oxide on different conditions. So if you can represent this, you can also pictorially draw this as this schematic illustration. So you can see the left one. The left one is the gas phase, gas phase baru nak masuk. And the second there is the surface of silicon dioxide as it grows. So maksudnya the second portion tu is the oxide thickness, and the last boundary there is actually the surface of the silicon wafer. Okay, there are three steps as we discussed just now. So the first one is the flux F1, which is due to the gas transport. So assuming your process uses dry ox or dry oxygen, so you're going to have your oxygen atoms from the gas as your transport flux. Okay, that will be your F1. So your F2 will be the diffusion flux through SiO2 as the silicon grows. So that will be labeled as F2. Okay, the moment you have your oxide on. So F3 is the reaction flux at the interface of the silicon. So the moment F2 to reach the surface of silicon, so we're going to have F3. So apa yang sampai tu dia akan react with the underlying silicon, with the existing silicon on the surface yang dah masuk dalam sekarang ni, to be able to continue the reaction. Okay, so we call the concentration of the gas as Cg, concentration of the gas reaching the oxide surface as Cs, oxidation concentration of the oxide of the oxidant, if you like, at the surface of the silicon within silicon oxide, C0, and then C1 is for the concentration of the reactant at the surface of silicon, Ci, okay. The XOX there is the thickness of the oxide grown through the process, okay, grown through the process. So we get kind of flux 1, flux 2, and flux 3. So F1, F2, and F3. So mathematically, they can be represented as this. F1 is equal to Hg. Hg is the mass transfer coefficient, centimeter per second, times Cg minus Cs. So you go back to the schematic there, Cg minus Cs. But kita start dengan gas punya phase. So the moment the gas phase hits the surface of the oxide, it's called Cs. So Cg minus Cs times Hg will be giving us F1 or flux 1. Flux 2 will be given by negative D diffusivity, d dx C, right? C there is given by C0 minus C1. C0 is the concentration of the reactant in the oxide at the surface, even though they are at the same interface, minus, minus Ci. Ci is the next one, the concentration of the reactant at the surface of silicon. Maksudnya satu atas silicon dioxide, satu dekat bawah silicon dioxide, over XOX. XOX is the thickness of the oxide. So you're going to have your times diffusivity of the reactant. So that will give us the F2. And this F2 is actually derived from Fick's law of solid state diffusion. Fick's law of diffusion. Okay. So F3 is the final flux where the reactant already reached the silicon surface. So Ci there, Ci. So that will be given by Ks. Ks is the surface reaction rate constant times Ci. Ci is the concentration of the reactant reaching the surface of silicon. Okay. So this explains the 3 steps of the Dilgrove model. Okay. The first one is the gas transport flux. Second one is the diffusion of the reactant or the oxygen atoms through SiO2 that's existing on the silicon surface. And finally, the F3 is given by the flux, reaction flux at the interface of the silicon the moment oxidants reach the silicon surface to continue the reaction. Okay. So ni Henry's law yang kita pakai untuk relate during F2 punya flux calculation. You can see later on Henry's constant, partial pressure of the oxidant at the surface, and you can also relate this to the equation below. Okay, ni dia punya derivation lah. How do we get to the final one? So at steady state, F1 is equal to F2 is equal to F3, or 1 is equal to 2. Ini dia punya detail of this, you can see later on. This will be helpful if you need to do calculation related to the Dilgrove model when you are given certain constant and thickness and diffusivity of the material at particular time during the process. So you might be required to calculate the flux, the thickness, and so on and so forth. Okay, so the flux, to be able to calculate the oxide thickness over time in your process, whether it's dry ox or wet ox, so you have to convert the flux, which is given by this Ks Ca over this denominator. So the flux has to be converted to thickness. Okay, the punya representation is this F. If you can see the figure on the left, down left there, oxide thickness, then the flux, incoming flux, and then silicon is on the right. Delta T is the change of thickness over time. Okay, so N1 there in the equation is given by oxygen molecules available per unit volume material in order to form SiO2. So you need to times ddt because it's time dependent, and times the oxide thickness. Okay, so your N1 value will be different if you use dry ox or wet ox process. So if you use dry oxidation, where gas is the precursor material, so your N1 in the equation will be 2.3 times 10 to the 22 per cm cube. Whereas if you use water vapor, your N1 will be double, 4.6 times 10 to the 22. Okay. Nanti kita akan tengok if you encounter any calculations for thermal oxidation involving Diel growth. Right, you will see later on if you relate back to the curve just now, where, so I guess I can do in the next page, where you can see the linear part and the parabolic part where it slows down. So you'll see the dependence of your coefficient B and A here. B and A is the coefficient. So when you have your small t, small time, which reflects lower oxide thickness, the XOX there will be given by B over A times T. This one is the linear region of the growth. And the moment you have larger oxide thickness or longer time or large T, so it will be limited by square root of B times T. So graphically, it can be represented by this. You have your oxide thickness on your y-axis and your growth time, if you like, on the x-axis. So you can see the two phases there. The first one is when your growth rate is actually proportional to t. Okay, in the linear region, first region is the linear region. So that's when you just started your thermal oxidation process. So the moment you hit the tempat dia nak turning point to the parabolic stage, so it's called it already goes into the parabolic model. So where your reaction is actually limited by the coefficient given in the previous slide. Okay, so it will slow down because at this point kat tengah ni, can you see the cursor? Just checking. Nampak cursor tak? Okay, good. So I'm pointing at the transition between the two phases. So at this point, your oxide thickness is thick enough to force your oxidants to diffuse through them to be able to get to the oxide. Maksudnya, if you work on this stage first, this one, okay, at this 0 point, kat 0 sini you tak ada apa-apa lagi on the surface. You just have pure silicon to start with. Then the reaction started, then developed over time. Then at this point, maybe it hits 50 nano or so. Then bila you start at 0 tadi, I forgot to mention, your reaction here is limited by number of atoms available on the surface. That's where the difference of 100 and 111 comes in. So the moment you have your oxide thicker over time, at this point, your reaction will be limited by the diffusivity of your oxidant through the oxide to get to the silicon. Okay, that's why it turns into parabolic. So it's about they can travel through they can diffuse through the oxide to be able to get to the silicon to continue the reaction. Okay. So oxide growth rate slows down with increased oxide thickness. So your DDT of your oxide thickness is given by B over A times 2 times oxide thickness. Okay. This one will become clearer if you do the calculation later on. So this Diel growth model can also be represented as this, if you like. So the left one is the first step when you just started the reaction. So walaupun you nampak oxide, guys, do actually need oxide yang masih thin, just to compare thin oxide and thick oxide. Thin oxide is on the left, thick oxide is on the right. So thin oxide is when you just started the process. Thick oxide is when you are already into the process. So for the left one, A, interface reaction is the rate limiting step. So where number of atoms are the defining factor to determine the growth rate of the oxide. So dia punya C tu pun sama, CG, and you can see C slightly different, tapi dia punya meaning dia sama. So you can use different C if you like, as long as they make sense. Cumanya they have to be explained well. So on the right hand side, your reaction is limited by the transport of oxidant. So either it's from your dry ox or wet ox. So the diffusivity through the oxide to get to the silicon. So that's when it drops drastically. Okay, drop drastically dia punya curve ni before it reach the silicon. So that actually hits the parabolic stage already. So this is another representation of the P and B over A, the dependence on the parameters of the process. Nanti kita akan pakai this for your calculation. Oh, what's the time now? Oh, 43 already. Let's go for a few more minutes. We can also see the effect of temperature on the rate constant, B or B over A. So they are rate constants. Okay, B signifies your parabolic constant. B over A is the linear constant. So maksudnya your constant for your first phase is given by B over A, where you go like that, and then the moment it hits the parabolic stage, the constant is called B. Okay. In these two graphs, you can see the dependence of your parabolic rate B or linear rate B over A against different oxidation temperature. So if you look at the x-axis in both graphs, so the left hand side is where you run your process at a higher temperature, and the right hand side is where you run the process at lower temperature. Sebab dia punya axis itu is 1000 over T, 1000 over T. So the higher the temperature, the more left you gonna get. Okay, so that's why you see your linear rate or parabolic rate on the left, linear rate on the right gets higher when you run at higher temperature. Then when you run your process at lower temperature, it's gonna go lower. So you punya constant ni pun akan bertukar dengan temperature. So then when you want to run your process, you need to know, for example, if you look at 900 degrees C, okay, let's look at the left graph, parabolic rate, 900 degrees C. Tengok apa beza antara wet ox for H2O there dengan dry ox. Yang mana yang will give you higher parabolic constant at 900 degrees C? Is it wet ox or dry ox? Tengok kat graf yang bawah tu, bawah kanan. Sorry, bawah kiri. Bawah kiri 900 degrees C. So 900 degrees C is here. So if you compare wet ox and dry ox, which one will give you higher parabolic rate constant B? Gimana? Wet ox, right? So it's very straightforward. Wet ox is going to give you higher parabolic rate constant for B. And in fact, if you look at the right hand side of the graph, 100 degrees C juga. So if you look at the linear rate constant B over A, so still wet ox will give you higher rate. So expect. So maksudnya apa yang you expect? Kalau you run process oxidation at 900 degrees C for say 1 hour, then which oxidation you expect to give you higher thickness? Will it be the wet ox or the dry ox? Yang mana yang you akan dapat higher thickness? Which one will give you higher thickness at 900 degrees C? Wet. Sebab wet punya rate is higher kan? So wet punya rate is higher than dry. So it's higher by that much. So you can compare on your parabolic rate constant graph or linear rate constant graph. And kalau you nak design the process, for example, you can also use this parameter. For example, kalau you nak run at 1000 degrees C, then you can get the value of your B over A, then you can get the value of B at whatever temperature and whatever time. Then you can plug in into your degrowth model, and then you can predict what's your targeted oxide thickness after the process, okay, by using the equation. So this is what is meant for. Right, one more. Each of the coefficient b and b over a has an Arrhenius relationship of this type. D equals to d naught exponential activation energy over kT. Then you can compare your wet ox on the left and dry ox on the right. Okay, you boleh tengok lah untuk 100, 111, what is the activation energy, what's the d naught of the process. Then you can actually use this calculation as well. Okay, how many more? I think I'll just stop here. Okay, so the essence for today is we learned about the Dilgrove model, which consists of 3 steps. So you can revisit this page. What are 3 main steps? So the first one is the oxidant, either is water vapor or dry oxygen gas, reacts with the silicon interface where you have no oxide at all. Then the silicon is going to be consumed by the 55%, 45% rule. And then the moment you have your oxide already grown on the surface over time, then the reaction will be limited by the effusivity of the oxidant through the oxide to be able to continue the process. So mathematically can represent this Dilgrove model by 2 main stages. So the first one is linear, where you don't have your oxide yet. So as the process grows, you're going to hit your point where the reaction is going to be parabolic. It's going to be slowed down by the diffusivity of your oxidant through the oxide. And finally, you can get your final oxide thickness if you use this equation and you know all the parameters to be able to design your process. Okay, so is it okay so far? It will become a lot clearer when you do your calculation, plugging your parameters into the equation to be able to get your thickness. So do you get the essence of the process? Dilgrove model? Is it okay? Okay or not okay? So far, okay? Okay then, alright then, I'll see you tomorrow, inshallah. So, bye for today. Take care. Assalamualaikum.